Section: Introduction. In this section, we have discussed the widespread use of large language models, LLMs, in various sectors like education, science, and media. It has been challenging to measure the extent of this use and understand how generated text is impacting information ecosystems. Differentiating between LLM-generated text and human-written content is becoming harder, with studies showing that even experts struggle to distinguish between the two. This poses a risk as misleading generated text can be mistaken for reliable information. Research has shown that AI-generated content, such as medical abstracts and news articles, can deceive AI detectors and readers. At a larger scale, LLMs can unintentionally amplify biases in the text, affecting hiring decisions and cultural representations. Analyzing LLM output collectively reveals trends that are not apparent when looking at individual instances. Therefore, it is crucial to evaluate LLM-generated content at a broader level to understand its impact accurately. To address this need, we introduce a new method called distributional GPT quantification to monitor AI-modified content in information ecosystems efficiently. This framework focuses on estimating the proportion of AI-generated or modified content in a dataset without analyzing each instance separately. By combining known human-written and AI-generated text, we can estimate the amount of AI-generated content accurately. Our approach is significantly more computationally efficient than existing AI text detection methods while providing more precise estimations. We demonstrate the effectiveness of our method by analyzing the occurrence of specific adjectives in recent conference reviews, showing that AI-generated texts exhibit distinct patterns compared to human-written reviews. By applying our framework to various AI conference reviews and scientific journals, we identify a notable presence of AI-generated content in conference reviews post the introduction of ChatGPT. Through our study, we aim to shed light on the implications of AI-generated text in information ecosystems, highlighting where and how it differs from expert-written content. Our method offers a simple yet powerful way to estimate the prevalence of AI-generated text in large datasets accurately. Section Summary. In this section, we introduce the challenges posed by the widespread use of large language models, LLMs, and the difficulty in distinguishing AI-generated text from human-written content. We propose a new framework, distributional GPT quantification, to efficiently monitor AI-modified content in information ecosystems at a population level, demonstrating its effectiveness through experiments and simulations. Our method estimates the proportion of AI-generated text in a corpus by leveraging historical data and a maximum likelihood estimation approach, showcasing its application in analyzing reviews from top AI conferences and scientific journals. Section: Related work. In this section, we discuss various methods for detecting AI-generated text. We start with zero-shot LLM detection, which focuses on identifying text created by language models without direct access to the model itself. This approach relies on analyzing specific characteristics of the text, such as entropy, log probability scores, and n-gram frequencies. Different techniques like Detect-GPT and DNA-GPT have been developed to improve detection accuracy by examining features like negative log probability curvature and n-gram differences. However, these methods are most effective when the internal workings of the language model are known. Since many commercial models are not open source, researchers often use similar models as proxies, which can limit the effectiveness of detection methods. Another approach is training-based detection, where a model is fine-tuned on datasets containing both human and AI-generated text examples to differentiate between the two. Contrastive and adversarial learning techniques have been employed to enhance the robustness of classifiers in detecting synthetic text. Despite these advancements, challenges such as overfitting and bias still exist. The effectiveness of publicly available tools for mitigating AI-generated content risks has been debated, especially following OpenAI's decision to discontinue its text classifier due to low accuracy. We also explore LLM watermarking as a method to embed detectable signals directly into text for identification purposes. Watermarking techniques range from modifying existing text to integrating watermarks into the model's decoding process. While watermarking can improve detection, concerns about its impact on text quality and coherence have been raised. In our work, we propose a novel method that estimates the proportion of AI-generated text in a corpus without classifying individual documents or sentences. By focusing on the overall corpus, our approach enhances stability, accuracy, and computational efficiency compared to existing methods. Section Summary. In this section, we explore various methods for detecting AI-generated text, including zero-shot detection and training-based detection. Zero-shot detection relies on analyzing metrics like log probability scores and n-gram frequencies, while training-based detection involves fine-tuning models on datasets containing both human and AI-generated text. Additionally, we discuss the concept of LLM watermarking, which embeds detectable signals directly into text to identify AI-generated content, highlighting the challenges and potential implications of this approach. Section: Overview of our statistical estimation approach. In this section, we outline our statistical estimation approach. We are aware that LLM detectors can sometimes have inconsistent performance. Instead of directly classifying each document in the corpus and counting occurrences, we opt for a maximum likelihood approach. Our method consists of three main parts: generating training data, estimating document probability distribution, and calculating the final estimate of the fraction of text that has been significantly altered or created by AI. The process is illustrated in a figure and can be summarized as follows. We gather writing instructions given to human authors for their original corpus, such as peer review instructions. These instructions are used as prompts in an LLM to create a corresponding set of AI-generated documents. By analyzing both human and AI document collections, we estimate the reference token usage distributions. We validate the method on synthetic target corpora with known proportions of AI-generated documents. With the estimates of the token usage distributions, we employ maximum likelihood estimation, MLE, to determine the fraction of AI-generated or modified documents in the target corpus. The subsequent sections delve into each of these steps in more detail. Given a set of documents drawn independently from a mixture, the log likelihood of the corpus can be calculated. With known token usage distributions, we can then use MLE to estimate the fraction of AI-generated documents. This marks the final stage of our method, requiring accurate estimates for the token usage distributions. To generate the necessary training data, we need historical data for estimating the token usage distributions. We assume access to reviews containing only human-written text, along with associated review questions and papers. This collection of documents is termed the human corpus. To create the AI corpus, we input reviewer instructions and associated papers from the human corpus into an AI language tool, prompting the LLM to generate a review. The texts produced by the LLM are compiled into the AI corpus. Our framework demonstrates moderate robustness to variations in LLM prompts. Estimating the token usage distributions directly for the vast space of all possible documents is impractical. Therefore, we simplify the process by representing each document as a set of token occurrences. We estimate occurrence probabilities for human and AI document distributions accordingly. By defining the presence of a token in a document, we can estimate the token usage distributions. Our token vocabulary comprises adjectives, and the estimation involves considering the absence of adjectives in documents. The outlined steps enable us to estimate the fraction of AI-generated documents in a target corpus. We also present a validation method by partitioning human and AI corpora for training and validation. By sampling documents from both partitions and computing MLE estimates, we can verify the system's performance and establish confidence intervals for the estimates. Section Summary. In this section, we present our statistical estimation approach for detecting AI-generated text in a corpus. We use a maximum likelihood approach with three main components: training data generation, document probability distribution estimation, and computing the final estimate of AI-generated text fraction. By training on human-authored documents and AI-generated text, we estimate token usage distributions to accurately identify AI-generated or modified documents in a target corpus. Section: Experiments. In this section, we applied our method to analyze peer reviews of academic machine learning, ML, and scientific papers. We presented our findings visually, while detailed numerical results and additional experiments can be found in the appendix. To gather data, we collected review information from major ML conferences on open review, such as ICLR, NeurIPS, Coral, and EMNLP, as outlined in a table. More details about the datasets can be found in the appendix. We then tested the effectiveness of our method on semi-synthetic data, confirming that our algorithm accurately estimates the proportion of LLM-generated texts in mixed validation sets with a prediction error of less than 1.8% across various ground truth scenarios for ICLR 23. Even though our model was trained solely on ICLR data from 2018 to 2022, it showed resilience to moderate topic shifts seen in NeurIPS and Coral papers, with prediction errors remaining low for NeurIPS 22 and Coral 22. Comparing our approach to a BERT classifier baseline and two state-of-the-art AI text detection methods, all evaluated using the same criteria, our method significantly reduced estimation errors both within and outside the distribution. Additionally, our method proved to be substantially more computationally efficient during inference time and had negligible training costs compared to backpropagation-based algorithms. We then investigated the extent to which conference review text was altered by LLMs beyond basic grammar and spell checking. Our analysis revealed a notable increase in AI-generated sentences after the introduction of ChatGPT in ML venues but not in Nature journals. The results, depicted in figures with error bars representing 95% confidence intervals, showed a marked rise in estimated values across major ML conferences post-ChatGPT release. Notably, ICLR experienced the most significant increase, followed by NeurIPS and Coral. EMNLP had the highest estimated value, likely due to NLP specialists' early familiarity with LLMs. Furthermore, we trained a separate model for Nature portfolio journals and found no significant increase in estimated values post-ChatGPT release, indicating a different response to AI tools in broader scientific disciplines compared to the field of machine learning. Section Summary. In this section, we applied our method to analyze peer reviews of academic machine learning and scientific papers. Our results, presented graphically, show that our algorithm accurately estimates the proportion of AI-generated text in mixed validation sets with low prediction errors across various conferences. Comparing our approach to existing methods, we significantly reduce estimation errors and computational costs, demonstrating the effectiveness and efficiency of our model in identifying AI-generated alterations in peer review processes. Section: Robustness to proofreading. In this section, we conducted a robustness check to ensure that our method can detect text that has been significantly altered by AI, not just simple grammar corrections. We tested this by using peer reviews that were edited by ChatGPT for typos and grammar. The results showed a slight increase in the detected changes, but it was much smaller compared to the changes seen in real reviews. We also explored how reviewers use language models, LLMs, to expand their review outlines. We analyzed our algorithm's ability to identify when LLMs are used in this way. By condensing peer reviews into brief outlines and then expanding them using LLMs, we simulated a two-stage review process. Our algorithm accurately predicted the level of LLM expansion, indicating its sensitivity to detecting this type of usage. Furthermore, we observed a slight increase in detected changes for reviews submitted shortly before deadlines, suggesting reviewers may rely more on LLMs when time is limited. Additionally, we found that reviews with scholarly citations tended to show lower levels of LLM usage, indicating that LLMs may struggle with including academic references. Moreover, we discovered a negative correlation between author replies and ChatGPT usage, implying that authors who engaged more actively in discussions were less likely to use ChatGPT for their reviews. This raises questions about the impact of LLM usage on the quality of feedback and the diversity of perspectives in peer reviews. Lastly, we investigated the potential homogenization effect of LLM-generated text on peer review feedback. Our analysis revealed that reviews aligned closely with LLM-generated text tended to have higher detected changes. This suggests that LLM-generated text may lead to a standardization of feedback, potentially limiting the diversity of ideas and perspectives in peer reviews. Section Summary. In this section, we conduct a robustness check to ensure our method can detect substantial AI modifications in text by comparing peer reviews edited for typos by ChatGPT. We also analyze our algorithm's ability to identify when reviewers use LLMs to expand brief outlines into detailed reviews, finding that our approach closely matches ground truth values. Additionally, we explore effects such as increased LLM usage near deadlines, lower LLM usage in reviews with scholarly citations, and the potential homogenization of feedback due to LLM-generated text in peer reviews. Section: Low Confidence Effect. In this section, we explore the low confidence effect. We observe a negative correlation between reviewer confidence and ChatGPT usage, as shown in Figure 16. One possible explanation is that incorporating language models, LMs, into the review process may create a sense of detachment for reviewers from the content generated by AI, leading to reduced personal investment and confidence in the content's accuracy and relevance. We introduce a method to estimate the proportion of AI-generated documents in a large corpus by leveraging historical documents. Prompts from the historical corpus are input into a large language model, LLM, to generate a corresponding set of AI-generated texts. By comparing the distributions of AI-generated and human-written texts in a mixed corpus, we can estimate the likelihood of AI-generated content in the target corpus. The estimate for Figure 16 is determined by maximizing this likelihood. We outline specific techniques for estimating text distributions based on token frequency and occurrence, as well as a validation method for assessing system performance. Applying this method to conference and journal reviews before and after the introduction of ChatGPT reveals that a notable portion of sentences in machine learning conference reviews underwent significant AI-driven modifications, while such evidence is less prominent in Nature reviews. Furthermore, we demonstrate how this method can aid social analysis. We find that reviewers are more inclined to use generated text for last-minute reviews, resulting in fewer author responses compared to reviews composed entirely by humans. Generated texts tend to offer less specific feedback or references to other works and are associated with lower confidence ratings. Additionally, corpora containing AI-generated text exhibit reduced linguistic variation and epistemic diversity compared to unpolluted corpora. It is important to note that concerns regarding the presence of ChatGPT in peer reviews extend beyond our study, including privacy risks associated with sharing unpublished work with a privately owned language model. While our study primarily focuses on GPT-4 for generating AI texts, we find that similar results can be obtained using alternative LLMs like GPT 3.5. We recommend selecting an LLM that closely aligns with the language model likely used to generate the target corpus. Our method, while not providing direct evidence of reviewers writing entire reviews with ChatGPT, emphasizes the need for transparency in estimating the AI-generated content in the final text. We hope that our findings stimulate constructive discussions within the community about the implications of LLM use in scientific publishing.